Okay, we're going to do quiz 5.3. On the lecture for this, I tried to cover a lot of things, not just a new technique of doing definite integrals, but also making sure you saw a lot of different things that come up when you try to do substitution. So they didn't ease in, I didn't ease you into it then, and you can just follow along and what I was doing. But here, since you're working, in theory, you're supposed to be working on the quizzes on your own, struggle through it, and then see the answers afterwards. So here I built it up more slowly and more like a homework. So it starts real simple, possibly even so simple that you forget how it works. So let's do number one. Number one, you're doing definite integral. 3, just a constant, and you have to remember your antiderivative of a constant is just that. So that when you take the derivative of 3x, it's just the coefficient 3. Plus c if it's an indefinite integral, but it is not. You're plugging in x equals 1 and x equals 4, the upper one first. So 3 times 4 minus 3 times 1 gives me 9. And that's it. Translation, do I want to translate this? Yeah, I mean, it's a constant function of 3. So your function is this. F of x is a constant 3. You're trying to find the area under the curve between 1 and 4. And this one has a nice geometric interpretation of an area of a rectangle, like 3 with 3. Okay, but anyway, you don't have to do that. You will be doing the areas in the later problems, which is just doing this again in a different context. 2. 0 to 2, and I got a different variable. Nothing different about that. It should have if you have a function in terms of t, at this level at least, it'll be with respect to t, so it'll have a dt there. Just a different variable, so everything's t. It does matter when you start combining multivariable and you have x and y in here, and you have a specific variable dx or dy there, and then you have to handle it differently. It's called partial fractions, but we're not doing that here. Okay, power rule. There's just a polynomial. I'm just doing power rule all the way down. T cubed minus t squared plus t. I'm going from 0 to 2. And so now it's just me doing a lot of arithmetic. Plugging in 2. So that's the antiderivative at when 2 is plugged in, minus 0 cubed. I mean, you don't have to, if you recognize it's going to be 0, you can just omit that, but yeah, make sure you're doing the upper limit of integration plugged into the antiderivative minus the lower. Okay, so that's all 0, and I just get 8 minus 4 plus 2, 6. 6 is my answer. Okay, next one. Let me see if I have room here. Can I fit it here? Yeah, we talked about how to handle weird powers, particularly half powers. So let's do this. 9 to 16 of the square root of y. Okay, I'm gonna fly through this a little bit. So that's y to the 1/2 because we've done this before. Y to the 1/2. I'm gonna treat it as y to the half, but I'm not gonna bother to rewrite it. Bump up the power by 1 becomes y to the 3/2. Divide by that 3/2, and that's the same thing as multiplying by the reciprocal. So that's your antiderivative of y to the 1/2. And now I'm plugging in 9 and 16. I got to do 16 to the 3/2. And last time I factored out the 2/3, but I wanted to make sure you understand that. When I do that, it's because each one has 2/3 times that 16 to the 3/2 minus the same method of 2/3, 9 to the 3/2. But in the past, in the notes, I just factored out ahead of time, so that's the same thing. Main thing is I got to focus on the 16 to 3/2. That is the square root of 16. That's a half power, and I'm cubing it. Same thing here. The half power is the square root of 9, but the 3 on top means I'm going to be cubing that. And these are designed to work out nicely. That's 4 cubed. That's 3 cubed. Multiplied by the 2/3 from that coefficient there. Don't lose track of that. Let me see, 64 minus 27, wrong, 64 minus 27, 37. That's 37, let me write it out. 2/3 times 37, I'm going to put that over 1 to do multiplication of fractions. 37, 3 goes into 37? Nope. So I'll just rewrite it as a single fraction. 2 times 37 is 74, divide by 3. That's reduced already. 74 over 3 is our answer. All right, moving on. Number 4. So far, no substitution. Do I need it here? If you had a lot of terms of complicated denominator, you probably set your u to be your denominator. If you set your u to be the top, if you set your u to be the top, you won't have to account for the bottom. And if you think about it, no, you don't need to, because this is a situation where we have a monomial on the bottom, single term, single power of x, and therefore you can break up the numerator and simplify into 3 separate terms, none of them fractions, or, well, hold off on that, one of them fractions. I'm going to do it quicker than I did before. It's going to be 3x squared for that first term divided by x squared, minus just a 7 constant for that middle one, minus 4 over x squared. And since I know I'm going to be doing the antiderivative, and that does apply to the power rule, I'm going to be rewriting it as x to the negative 2 and working with that. That's just rewriting it, simplifying your integrand. So I have not done my integration yet. I have to do my antiderivative next. It's going to be x cubed minus 7x, and I got to bump that up by 1. It's going to be x to the negative 1 divided by negative 1. We'll cancel that. I'll get that. And now I'm plugging in 1 and 4. Okay, just again arithmetic. Let me get this out of the way. Oh, my rag is so soaked with ink. Anyway, 4 cubed minus 7 times 4 plus, I probably should have, that's 4 over x. I do the power rule on that, and I get a negative power, and I've said in the past, you can just leave it like that, or you can rewrite it as 4 over x. When you're plugging stuff in, you probably want to rewrite it as 4 over x. I'm not going to rewrite it, but that's what I'm plugging in there. All that's my antiderivative at 4. I'm going to use brackets for my antiderivative at 1, so I'm careful with my minus sign applying to all of those terms. 1 cubed minus 7 times 1 plus 4 over 1. All right, 64 minus 28 plus 1 minus 1 plus 7 minus 4. Can I do that in my head? I don't really want to. 39. 39? Yep. All right. Can I fit the next one over here? Nah, it's going to take a little bit of work. Let me clear the whole board. This one I have x minus 2 on the bottom, so unlike a monomial where I can chop it up, I can't chop up the bottom. It doesn't look that bad, but this is a tricky one. I think I've done 2 examples that work out in this way. We'll see when we start working it out. But I have x on top, x minus 2 on the bottom. You cannot split it up like that. You can't break up a denominator like that. That does not work that way. You can break up a numerator like we did the last problem, but not the denominator. This is not a nice one. I did mention often, no, 3 and 5. When you have a denominator that has multiple terms, Sometimes you want to do u substitution and set u to be the denominator. That's a good start to try. It doesn't mean it's going to work. So I got u is equal to x minus 2. That's my denominator. I'll need to translate dx to du, so I take my derivative of this equation. Du is just equal to dx, so that right there is going to be just a plain du. That's u, that's du. You have an extra x that's unaccounted for. So this is a trick where, I won't say it's a trick, but you can actually solve this for x and express it in terms of u. And it's not doable when you have like x squared and you got to do square roots or cube roots, but here it's a pretty clean linear expression, and you will be able to just rearrange things essentially to find that x can be expressed as u plus 2. There it is. I got every piece. So the x minus 2 on the bottom is just u. The dx is just du. And an extra x there, I could solve it for u, and I got u plus 2. So it changes it a little bit. It's still got, you know, an polynomial with just 2 terms and just a single value, similar, but now your single term polynomial is on the bottom, and your polynomial with 2 terms is on top, and that allows you to do what we did in the last problem, which is break it up. So I'll be looking at it like that in a little bit, because I have not done, this is a definite integral, and I said what I'm going to be doing in the future, well, from here on out, is I'm going to change my bounds every time to u values. So that's x equals 3, and that's x equals 5, and so I'm not even going to write that. Yeah, you guys know what I'm doing. I did it for my notes, but here I'm just going to go mentally. U is equal to, u is equal to. And it's pretty simple. But anyway, when x is 5, u is 3. When x is 3, u is 3 minus 2 is 1. So when x is 5, u is 3. When x is 3, u is 1. So these are my new bounds in terms of u. Therefore, when I do my antiderivative in terms of u, I'll just be able to plug those in directly, and I'll never have to go back to x if I do it this way. If you leave them as x bounds and you don't change your bounds, that means at the end you will need to convert your antiderivative back to x using this. Okay, let's see. I should write the u's to remind myself which way I'm doing it. Okay, antiderivatives of 1. And here it's 2u to the negative 1, but that's a power that does not work with the power rule. That is your natural logarithm. Okay. I'm going to be plugging in 3 and 1 in place of there, so the absolute value won't matter because they're positive anyway. Go up here and do it. Anyway, it's going to be plugging in 3 into this whole expression. 3 plus ln of 3 minus, plugging in 1 in that expression. 1 minus ln of 1. Note that ln of 1 is 0. They will expect you to reduce that to 0. Then I'll have 3 minus 1, which is 2. That term is gone. And I'll have ln of 3. And that's it. Oh, what happened? Shit, I lost something. Back up. I'm wrong. Completely lost something. This 2. You caught that, great, but I messed up anyway. It's fixable. Completely fixable. Anyway, that 2 there, it's 2 times, I'm thinking of it like this. The 1 over u is a ln, the 2 is a coefficient. I'm gonna put it back the way it was, but that's what I should have been. I should have kept that 2. Let me redo it from here. It's fixable, but nah, let me just back up. So 2 ln of u, and I'm gonna plug in 3. I'm gonna plug in 1. ln of 1 is still 0, nothing's changed about that. 2 times 0 though is still 0. then I'll have to distribute this minus sign. It'll be 3 minus 1, which will be 2, plus 2 ln of 3. And that is it. So I was missing that extra 2 there from that coefficient that I missed. Another way to rewrite this, so again, one of those things where your answer might look way different from the back of the book. They might have an answer of ln of 9. You're thinking, I got ln of 3, how'd they get ln of 9? Well, it's because they're using a rule for logarithm where they can move that exponent inside, and it becomes ln of 3 to that power, 3 squared. So you can condense that coefficient, make it into a power, and pull it inside a logarithm, using that rule for logarithms to get a different form of an equivalent answer. But don't worry about it. I mentioned that just so in the future, if you encounter that situation with logarithms in your answer, it is very common for the back of the book to have a different form of it that looks so different, but it's really not if you apply the rules for logarithms. Number 6. Oh, that was number 5, by the way. E squared. Alright, that's one of those where it looks weird, but no, I've got logarithms. I'll probably be plugging that into a logarithm. It'll cancel out, and I'll get a clean 2 out of it. So what I just said was, if in the future, if I end up having to plug that e squared into a logarithm, that cancels out. That's a log base e of that same base exponent will give you the exponent. So note that it won't say e there, but natural logarithm of e to any power is that power. I'll probably end up doing that. I'm anticipating that that's going to be used after I work this problem out. All right. Ooh. I'm definitely not going to, probably substitution. It's not looking clean at all. I can make u is equal to x, that x on the bottom, that's never going to do anything. Again, that just rewrites everything in terms of x, but does not make it any simpler. It's literally going to be the same thing, but with u's. I got an ln squared. If I set u to be ln squared of x, I have to note that that is interpreted as that. And then when I take my du, it's going to be, I got to do the chain rule line. 2 ln of x to the 1 times the derivative of that inside function ln of x, that dx. It does account for that x on the bottom, but I have a logarithm there, and now I would have too many logarithms. I have that 2, I have an extra one there, and the pieces aren't coming together if I set u to be ln squared. But note that you do get that 1 over x from the derivative of the logarithm. So just trial and error. Maybe I just do it without the square. Let's see. The du will be 1 over x dx. That looks good because that'll account for that x dx. That'll just be u squared. And then I got the 6, so I think I'm good. I'll change my bounds though. Well, let me make sure it's gonna fit. The pieces are gonna fit together. Okay, so what I got? The 6 I can pull out. That ln squared is u is ln, so that's just u squared. And then the 1 over x and the dx is right here. It accounts for du. So it's good. Yeah, that's definitely doable. So that worked. The pieces fit together. So using the ln of x is a substitution to go with there. My boundaries, this is a definite integral. Those were x boundaries there. And so I'm going to do this when x, I'm going to work it out a little bit more carefully than I've done for just numerical things. When x is e squared, u is equal to ln of x, so ln of e squared. And I just talked about that that means it's 2, simplifies, because the ln and e are natural, they're not natural, they're inverses of each other. X equals 1 is my lower bound. When x is equal to 1, u is equal to ln of 1, and that is 0. So my boundaries transform to u is equal to 0, u is equal to 2. Okay, that's still just rewriting things or doing substitution and rewriting in terms of u. I have to do the antiderivative. It's very common for people to get the process of the u's and then just treat that as the antiderivative and forget to actually do an antiderivative, so be careful. I got through, we got 6 there, so I'm going to get, well, just going to skip a step. But anyway, power rule on that, u cubed over 3, with that 6 it's going to cancel and get me a 2u cubed, and I want to evaluate that from u is equal to 0 to u is equal to 2, because I'm transferring my bounds to u. Plug it in, I get 16. Okay, just in case you ever start, where you work with a professor that does go back to x, does not convert the bounds. I did it once in the notes, and then I said I was just going to convert my bounds from then. I'll do one more time, just so you can see it one more time the other way. But if you're fine with that and you're okay, you can skip to number 7, just fast forward the whole video. I'm going to erase this stuff. Okay, if I don't convert my bounds, meaning I got to go back to x at the end, I'm still going to do a u sub. It's still the same u sub. Whatever worked there will work here. It's not that I'm doing any different technique. It's just a matter of when I'm going to convert those, what I'm going to do with those x's. Okay, so I'll have 6 u squared du, like last time. But the issue is now, suppose I choose not to convert my bounds. And again, people just leave it as 1 and e squared, they don't write x equals, and sometimes they lose track of what it is at the end and they plug into the wrong thing. My power rule on that, u cubed over 3, is going to cancel with that, so I'll get, once again, 2u cubed. Same thing, but I can't plug in e squared and 1 into there because this is u and these are x values. So what I need to do is I need to rewrite this antiderivative in terms of x using the substitution I did, u is equal to ln of x. So this is 2 ln cubed of x. That's my antiderivative. If this is an indefinite integral, I'd have to go to that with a plus c, and that would be it. I need an antiderivative in terms of x, and there it is. I'm doing a definite integral, so I'm going to be plugging in x equals 1 and x equals e squared. Alright, so e squared in there. Oops, it's cubed. And I'm going to talk about how to handle that, but and then ln cubed of 1. Keep in mind that this cubed here is a power for the entire logarithm, so goddamn logarithm. No, I'm going to go over there. I'm just going to condense this down. Let me backtrack a little bit and make some room. Okay, so we're going to 2 ln cubed of x. Sometimes they write the parentheses to emphasize x is your input to logarithms. If they don't put it, you assume that you assume it is anyway. Okay. So this square applies to the e, and that's inside the logarithm. And they'll cancel, but I have that cube. That cube's not going to be in the way because that cube is essentially outside. What that means is it's a whole function of the ln of e squared, the whole thing cubed. That's how that's interpreted. Same thing here. That's just ln of 1, all of that cubed. So you're just working out logarithms and then raising it to a power. So don't be fooled by where it's placed. That convention is interpreted as a cubed after you apply the logarithm to e squared. And when I apply, well, that's 0. And that's 2. And So what I end up with is, why am I writing so messy? 2, that's 2, I want to cube that 2, that's 2, that's 0 in there, and I want to cube that 0, and obviously that's 0, and I get 16. You'll notice that the steps that I did to convert those x's to e's, when I did up here to get those u's, here I just had to do it at the end, and it was a little more complicated and ugly and messier, but it's fine if you're used to that or prefer that way. Same answer as long as you're careful and as long as you know what you're doing. Okay, so I'm going to take a break. Alright, let's finish up this quiz. Last two problems are looking for areas under regions, and they're worded differently. Okay, number 7. So you don't want to sketch it accurately because the integral will handle any kind of issues generally. Well, nah. You do kind of know if it's waving up and down or going below the axis or things like that. Okay, anyway, we want that. It's good to know your general transformation, so very briefly. At this level, they expect you to have taken college algebra where you start with a general function, a square root function, or a parabola centered with a vertex to origin, or your x cubed, real quick, that's that, y is equal to x is a line, mx plus b. Sometimes they want you to be able to do y is equal to 1 over x, which is a hyperbola. What else, is that it? Anyway, they do this in college algebra, and then from there you build and you learn to transform things by shifting it left and right, up and down, stretching vertically, stretching horizontally. So this will be related to this function. The numbers inside is just stretching it and shifting it left and right. So we don't need it to be super accurate. You can look at your domain if you want. The 4x plus 1 has to be greater than or equal to 0 because it's a radicand under a square root. That means x has to be bigger than or equal to negative 1/4. That means the whole thing is shifted to, I'm going to just draw it here, but it's just basically going to be shifted to negative 1/4. It doesn't get shifted up or down. That would be like a plus 5 would shift it up if we're outside the radical. The numbers inside are shifting it horizontally. Anyway, that's a rough sketch enough to be able to do this. You don't need it any more than that. And you want to find between 0 and 6. So here's 0. Here's 6 somewhere. And again, I don't need to be accurate. I don't need to know what this y value is. I just need a general idea that it's just some sort of a curve sitting above the x-axis, and I want to find the area under the curve from there to there and interpret that as an integral. So rewriting this as an integral, I'm just integrating from 0 to 6 of that function dx, and that'll give me the area under that curve. So again, not an accurate graph, but just a general idea, so you can just know that it's just doing a definite integral. We will have to be a little bit more concerned when we're starting to do things where we're looking for the region bounded by two curves, and we'll have to know which one's on top and which one's below it and things like that. So we'll get to that. So we got to be a little bit familiar with the basic graphs. All right, anyway, this is what I'm doing. Let's see. I don't have an antiderivative for a square root of an expression or a function, so probably substitution. I do have one for if that's just a u and a square root of that. I can definitely do that because that's just the power of u. So I'm probably going to do that. Let u be equal to 4x plus 1. Maybe it's going to work, maybe not, but let's find out. I don't have any extra stuff, but I won't need it because my d is going to come out to a clean 4 times dx. I'll divide both sides by 4, move that 4 over, and I'm ready to go. Over here though. What am I doing? That's my radicand is u. My dx converts to a 1/4 du, so I have a 1/4 factor there. This could be applied to like a reverse chain rule with that 1/4 coming out, like I said way back, but I'm not going to get into that now. I'm going to convert my bounds though. When x, I'm going to do it in my head though. When x is 0, u is 1. 4 times 0 plus 1. When x is 6, u is 6 times 4 is 24 plus 1 is 25. 1 to 25, and I've done it in a different order than I usually do. 1 is my lower bound, 25 is my upper bound, and those are u values. Alright, I'm ready to go. The 1/4 can come out. I'm just going to pull it out here. I'm going to bump that up power by 1. That's 1/2 power. That's 3/2 divided by 3/2. It's the same thing as 2/3. Okay, so we've done things like this before. The 2's cancel, so I get 1/6. U to the 3/2. Oops, I should have wrote it over here. And I'm going to be plugging in 1 and 25. 25 to the 3/2, 1 to the 3/2. We've done this a couple times now. That's just the square root of 25 cubed, square root of 1 cubed. So it's going to be 125. That's going to be 1. And don't forget about that 1/6. I'm going to get 124 over 6, and I feel like that definitely reduces because they're both even. It's going to be 62 over 3, and I think that's reduced. 62 over 3 is the correct answer. That's the area under the curve right here. By doing a definite integral for those bounds and just integrating that function that's bounding that region. All right. Next one is similar to this. It is an area under the, or an area of a region. It is written differently. So I want to talk about this because sometimes it won't just be something bounded or below a curve down to the axis like that one. Sometimes there could be multiple curves and they're all bounded, and you have to look at what that region looks like. I have several curves. Y is equal to 3x squared. Here's what I wanted to know the general shape of that. Doesn't need to be super accurate. X equals 2 is another bounding curve, and the x-axis. So your y is equal to x squared is just your basic parabola. That 3 just stretches it vertically, so it'll still go through the origin. So if x squared looks like that, then 3x will just be 3 high, or the way you're just stretching it by 3. It doesn't really matter. The main thing is you know that it's still going through the origin. It's still going to be 0, 0, and it's just some sort of curve going up. That's all the details you need. Next, I gotta do it. So that's that curve right there. And in fact, I'm not gonna make that steep. I can scale it how I feel safe. So I'm gonna say it looks like that. But main thing you know, it's a parabola. Going through the origin is important because the x-axis is another of my bounding curve. So that line there is part of the boundary of my region. And the last one, I kind of already that. That's my x-axis there. I highlighted, and x equals 2. It's just a vertical line at 2. So 1, 2, right here. So it's these curves, this parabola, which goes on this side, this x-axis, which you can and then this x equals 2. And the region that's bounded by all 4 of those is that region right there. And so it's like the other problem. It's no different. It is down to the axis. It's just bounded by this curve from 0 to 2 basically. They didn't specify 0, but that's where this intersects, so that's the closing off of that region. The x equals 2, instead of putting an interval from 0 to 2, they mentioned that a bounding curve is this vertical line. But it's the same thing as just integrating or just treating it as an interval from 0 to 2. The curve above it, and we want the area below it, is the 3x squared. So it is just like number 7, the previous problem, except you have to do a little interpretation with different curves going different ways, but it ends up being the similar situation. It may not in the future, it might be a little more complicated, but here it was just pretty basic. X cubed from 0 to 2, plug it in, and I get 8. Yep, okay, but anyway, I just wanted to mention that form of it where they've got a bunch of horizontal or vertical lines in addition to a curve, but oftentimes it just boils down to the area under this curve between 0 and 2. All right, next thing we're going to be doing is I'm going to bounce around with the next couple of sections. There are 3 more sections in the chapter, 5, 4, 5, 5, 5, 6, but I'm going to pick out the applications that I want you to do. So each homework will be short. I think I might even skip 5.4. I'll look at what the applications are. We'll see.